Alrighty, are we live? Testing this out again. Yeah, looks like we're here. So hello and welcome. We're gonna actually revisit a problem that we were looking at the other day. So let me do that. So the problem we were looking at the other day was this largest divisible subset. And you know what? I need to actually go ahead and I need to close these blinds. This is way too bright. So we have these largest divisible subset, this largest divisible subset problem to look at. And we solved it the other day, and I thought that was a pretty good solution. And you know what? I just remembered I was supposed to exercise today. I didn't do that. It just struck me. But anyway, we'll do that tomorrow. Sorry, it's fine. Different subject for another time maybe. But what I wanted to look at was someone was talking about an optimization that you can make for this problem that I thought was very interesting, and it was very specific kind of an optimization. Excuse me, and I actually want to explore that. So the way it works is like the following. It would be, it's actually this isn't a, so yeah, so what we want to do is, I want to use an unordered, I'll explain in a moment. We want to use an unordered map, and we want to use an unordered set and an unordered map. And what we want to do to optimize this problem, it's going to be like the following. So I just want to check something quickly. Oh wow, that's a lot darker. Whoa. Whoa. Wow. What I want to do, I'll explain in a moment. So there's a small optimization we want to make here, and the idea goes like this. What's happening is, let me see if I can explain it. Just in English. I don't know. I was going to write, but I'll just try to just explain in English. So, or orally. So we're looking for the largest subset of numbers such that all the numbers either divide or are divisible. For every pair of numbers in that subset. How to explain this? So the property is that it's a subset. Considering the set of subsets of the list of numbers we're given, the set of subsets of the list of numbers we're given, the subsets that have the following property, the property being for every pair of numbers in that subset, let's call them A and B, either A divides B or B divides A, right? That's true for all the pairs in that subset. Of all the subsets in that set, or all those possible subsets, we want the largest one, the one that has the largest number of elements. And we wrote an algorithm to achieve that. And there's an optimization you can do where if it's a dynamic programming solution, and basically you kind of build information as you go. The pruning, the optimization to prune the algorithm is such that you can toss out pieces of information. You don't have to consider it again, and it's very clever. And the way it works is, if you know the largest element in the set, what the value of it is, and you know the current solution that you've got, like you've got a certain size subset that you said, okay, this is like the largest we know of at the moment, you can compare it to another subset that you might still be considering, and you could say, okay, how many multiples of that smaller subset of the largest element of the, because we're also building in such a way, we're building our sort of possible subsets that we're considering sort of in sorted order. So the last piece we looked at, is sort of the largest element of that set. And actually, I guess, yeah, let's do it this way. So the clever thing is we can actually toss out some of those subsets, because if we have a particularly large subset already, a large number of them, and we know what the largest value possible in the whole list is, we can say we need a certain number of multiples of the largest value to even possibly get close enough to the set that we're already considering. And if the largest value in the set is too small, then that means you won't ever be able to reach the set you've already got, if that makes sense. So basically you multiply, and the smallest value that you can have that you create another multiple is 2, right? You multiply by 2 to create another number. You can't multiply by an integer smaller than 2 to create another number, right? If you multiply by 1, it's just the same number. So it's got to be so basically, let's say your current largest solution is 5 numbers, and your current and the thing you're looking at is 2 numbers. The difference would be 3 numbers in between. And so you would multiply the largest value in the set of 2 by 2, multiply by 2 once, multiply by 2 again, multiply by 2 a third time, and you'd have multiply by 8, 2 raised to the third. And if that number, so whatever that number was, multiplied by 8, if your list, your sorted list, the largest element in that list is smaller, then it means you're never going to have, that set of 2 is never going to be large enough to even be equal to the set that has 5. So that's kind of a long-winded explanation, but basically you can prune out using this mechanism to prune out elements from consideration in the future, and that apparently optimizes this algorithm dramatically. So, and that was in the discussion, and I kind of missed that before, so I wanted to kind of code that in because yeah, I missed it. I missed it, and I was thinking, oh, I should give that a shot. I should give that a shot. So I'm going to show kind of a way to do that. So basically, I'm going to use the same algorithm that I had before, except it's going to be, instead of an array of solutions, of previous solutions, it's going to be an unordered map of previous possible solutions to consider. And we're actually going to delete portions of the map as we go. And we're also going to maintain a set, an unordered set, of elements that are going to be the indices to this map. So basically the idea is that we're taking the vector of vectors, or the vector of possible solutions, and instead of using a vector, we're using an unordered map, which still has indices. It's sort of like a pseudo array, except we can easily remove and delete sections of it. And then we're also, instead of using in this loop where we just kind of loop over from the beginning to wherever we're at over the solutions, we're going to actually have a set of indices that we're going to loop over and actually delete portions of it. So we're kind of going to skip parts of the array and the map. Really, it's a map. And the reason why we're using the unordered map, by the way, you may realize you don't actually need to use an unordered map to do this, is that I actually want to optimize a little bit on the memory as well. That's why I want to delete portions of the map too. So that's why we're going to use an unordered set and then an unordered map in tandem. So we'll say indices, and now we're going to say really it's x in indices, and then we say we don't need this index anymore. It really is this is the index, and the value is, hold on, I made a mistake. Oh, no, we're fine. That's okay. It's actually going to be nums of index. Yeah, I think that's correct. And then just see val modulo equals 0, index size. Just thinking if there's anything else I need to do here. And we're going to say indices dot insert this new index, which is, I have this iterator. It's going to be just iter index. That's really what we want to do. We can actually just do, keep this simple. Yeah, we're going to keep this, try to keep this simple. Or, yeah, just keep it kind of, yeah. So, okay, insert I, and solution pushback. Now we're not pushing back anymore. Oh no, we are. Yeah, the current solution, you do push that back. That's fine. So this, now we say it's not pushback, but it's I. Solutions of I is going to be equal to this current solution. And current solution is greater than red size, right? So we update our best possible so far. And now we don't have the pruning yet. So I think this should still work. Let me just see what this does. Hopefully this still works. Yeah, okay, so it still works. Right, this is just like a different way of setting things up, where it does the same thing that the previous code does, except now it's a little less efficient for a few different reasons. We won't go into details as to why. That actually might be because we're not using iterators, we're using direct accesses. I wonder why. I don't know. I actually don't know why it's that much less efficient. But it's less efficient. So now what we're going to do is add the pruning. So we say if solutions of index dot size is less than current solution dot size, we'll do it this way. Check. Yeah, actually, yeah, okay. And all right, the largest value is always going to be the nums.back, basically. So, and the largest value is less than 2 raised, we're going to use the power, 2 raise this difference. Actually, I should do it this way. Difference is going to be current solution minus solutions index dot size. So if this difference is greater than 0, right, it's the same thing as this check. And then we're going to say if this difference, if now we can do it this way, okay. Difference is greater than 0 and nums.back is less than power of 2 raise this difference times the largest value of the solutions index back. Really should be the largest value. If check is true. We're going to do a couple of interesting things. So, just thinking here. So, if the difference is non-zero, right? Then, which by the way, if it's 0, then yeah, we don't care, right? If we just updated to this. The deal is if it's non-zero, then we want to, we set it, I think this is it, right? This is the largest value in the numbers, it's because it's sorted. This is the largest value in that particular possible solution. Possible solution, because those possible solutions are also going to be in sorted order, just naturally. So that's also the largest value. If that largest value, if the largest possible value is smaller than this, then we can prune. So should prune, we'll say should prune. So we'll just do check, prune check, or just prune. If prune, then we're going to take our indices and we're going to remove or erase this particular index. And so we're not going to, in the future, we're not going to loop through it, and we're not going to loop over that index. And in that particular map, solutions.erase that index as well. Is this still correct? Let's see how we do. Ooh, I'm being a lot less careful here because we already solved it. So this is really, basically just using these as basically using these as, what do you call that? Basically using these as what do they call it? The test cases. I'm using their tests as like my own test cases, I guess, instead of writing my own test cases, which I technically could write my own, but we already got it, so I'm not really too concerned. Although this is kind of interesting. Why is it not correct, though, is the question. It's looks like a kind of runtime error. Excuse me. I wonder. This input. Why did this cause problems? Let's find out why. I don't actually know why. Could just throw I don't know. I'll just throw some. I don't know where it could be going wrong. I think it's. I'm not really sure. I don't really know. I want to say I shouldn't be using indices, I should be using the numbers themselves. You can do that too, it doesn't really matter. Really shouldn't matter. But something wrong here. Let's do this. Let's do it this way. It's like how many iterations before we run into a problem, I guess. Okay, what does this do? 0, 1, 2. No. That's not supposed to happen. What? 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is wrong. This shouldn't be happening. 0, 1, 2, and then 0, 1, 2 again. I don't know why that's happening. What's going on there? What is going on there? This loop is supposed to go just straight through, just 0 to the end. We don't modify I anywhere, do we? We don't. How could, why, what? What's happening? Why is this happening? Why is that? Where is I being set back to 0 again? That doesn't happen anywhere. We're not removing anything from nums. What is going on? I'm so confused. Hold on, what? If you comment everything out in this loop, this should be just one straight shot. What is going on here? What? Oh, that's why. Oh, I'm sorry. That's my mistake. Duh. That's okay. Alright, I'm not crazy. It's going insane. What's going on in my brain? Seeing things. So we get to 115, which is I don't know. Let's do it this way. See how we do here. All the way to 192 we get to. And it's not too far. And then something happens at 192. What goes wrong? Heap use after free on address. I want to say it's because we're looping through this set and we're deleting values from the set. I think that's why. Yeah, that's why. Yeah, I've done that before. I don't know of a good way around that though. I thought I was so clever too. I thought I was so clever. Being able to delete elements from this set. Okay. Now here's the question. Can we do it this way? Make it temporary and then modify the main one. Does that work? Oh, okay, it works. Let's see how we do. Yeah, so what I'm thinking, this should be create a copy constructor. You should, yeah, basically it should be a copy assignment. Should be copy assignment. So we copy it each time. I don't think that's much better though. I think that's like still pretty relatively inefficient to do it this way. My thinking was I was thinking it'd be pretty clever by sort of avoiding certain indices altogether. But creating this unordered set every time is like kind of inefficient. Yeah. You know what we could do? I could do it this way. We could do it this way. I have an idea. Well, yeah, instead of pruning, we'll do it. So we're not going to erase. We can erase from the solutions. That doesn't matter. We're going to say temp.insert. We're actually going to do it this way. I have an idea. Indices to skip. How about that? How about that? I still don't think that's much better. Actually. I still don't think that's much better. Okay, how does this go? How does this work? Okay, that's a lot faster. Yeah, okay, that's way better. Yeah, it seemed like copying that over and over again just seemed really bad. So we only delete things if we need to. Only push things in there if we need to. So this is mostly empty. Yeah, it's kind of gotta. It's a good thing I coded it because in my mind I was like, oh, this is like pretty easy. This is not too bad, but in practice it's like a little more involved than you think. And also, wow, that's a lot slower than I thought it was going to be. Really? Excuse me, really? That's kind of upsetting. That's almost frustrating. Really? Wow. Also, this could be optimized slightly. You can bit shift to the left diff number of times. That might speed things up a little bit. Hopefully, maybe not. No, this is slower. This is slower. You're kidding, really? Yeah, there's kind of a lot of expense rolled in there when you're dealing with using an unordered map and an unordered set. These are kind of expensive to manipulate. Shoot, man. I was hoping to use less memory, but didn't really do very much for the memory. Wow. This didn't seem to matter very much. It's pruning. The fellow who was describing the pruning mentioned that actually the pruning made the algorithm like extremely efficient, like way more efficient. Spent like 20 minutes on that too. That's not much more efficient. It's less memory. No, it's not less memory. It's hardly less memory. No kidding. All right, we could try something slightly different, which is unordered or just vector. Vectors, solutions, and kind of go back to what we were doing before, except still use these indices to skip set. See if that matters at all. So we don't erase the solutions anymore. And we still do solutions index. I think it's all the same, except solutions index. Pushback, current solution. Does this still work? Yes, it does. Okay, so that's faster. That's a lot faster. But that's largely faster because we're not using the unordered map anymore. And it uses less memory somehow, which is kind of funny. It's like kind of trying to avoid certain things, and it's faster doing it this way. we still need I? You can use, yeah. Just thinking if wondering if it's faster if we go back to iterators, because an array access is kind of slow here. Also, these array accesses. I don't know. It's definitely interesting that this didn't give me the 6 millisecond speed up that the fellow was describing before. I think it's because the expense that I'm going through to remove these indices is kind of excessive. It's just like a lot of extra effort to remove these indices, because we've got to maintain this unordered set that we're looping through repeatedly. I want to say something like that. I think that might be part of the issue here. Yeah. I don't really know. I don't know, man. I don't know. That's kind of strange. Is there a faster way to do this? Could actually use like a linked list instead of an unordered map. Yeah, you could do this faster, couldn't you? You definitely can. You know what to do. I know what to do. I know what to do. I got this. You ready? I have an idea. Okay, I have an idea. Solutions. Don't even use indices. And you're going to say auto reference X solutions. X is, that's confusing. Oh no, you can't do it that way, can you? Yeah, you can. That's fine. Call it key or key val, or just we'll call it Y. Just do X. I think you could do it this way. Okay. If Y divided by X is 0, val is the same. Right. If val divided by Y is true, and we're going to say X size is greater than current solution size, then we're going to say current solution is equal to X. And then this difference is going to be the difference in the current solution and X. Or we'll just say possible instead of X. Possible. I'm going to say key. It's like a key value. I want my variables to be a little more, have a little more to them, a little more description. So prune if that difference is greater than 0 and the largest value in the numbers is less than this possible set's largest value, which is actually the key, which we're going to bit shift to the left diff number of times, or multiply by 2. So if we prune, now we're actually going to go ahead and do the following. Oh no. What I want to do is swap this vector with the last vector in the solution set and pop it. Problem with that is if we do this for loop, we'll run into issues, I think. Yeah, it's super awkward. Can't do it that way. Alright, we can do it this way. This is a little awkward, but we can do it this way. Okay, there we go. Alright, now if prune, we're going to say standard swap of possible with solutions back, right? Excuse me, we're going to pop back. And then we're going to decrement j. So it's going to decrement j, this is going to increment j, and we're going to end up in the same spot again. Hopefully that makes some sense. And I think if we do that, then we don't need these indices to skip. But some clever kind of manipulation here in order to avoid all this index manipulation shenanigans that we were just doing before. So we don't have these indices anymore. Current solution, pushback value, solutions, pushback current solution size, update ret. Yeah, okay, let's do all that. Hey, it works. Does it work? Hey, still slower than what I had before. Ah, you're kidding. Come on, really? Less memory though. Not too much less, but yeah, slightly less memory. Okay, it's better. I mean, it's not much better. Yeah, we did 32 milliseconds before. Consistently 40 milliseconds. I don't know, man. Oh, there we go, 32%. We got that before, so we have an improvement, slight improvement. But there's not 6 milliseconds as we were expecting. Yeah, it's not as fast as we thought it was going to be. The guy who wrote the pruning routine said it was really fast. Yeah. It may be that we need to actually do better with our pruning. We actually can do better than this. We can say, instead of using a power of 2, we can actually use, well, use like a better pruning approach here. I get this feeling like this pruning doesn't do anything. I don't know, man. This is challenging. Also, this could be a pointer instead of an index, which may or may not matter. I guess it, no. Instead of doing all these array accesses, using an iterator might speed up a little bit, but probably not that much. Man, I don't know. I thought this was going to be faster. It's not very much faster. You know, not too much faster. It's actually a little bit slower, I think. So we had, well, it's a little faster, I think, actually. It's more consistently faster, but I don't know, man. Maybe we should go look at the discussion again. Shoot. We don't need these also. Yeah, there was a 6 milliseconds C++ beats 100%. Man. Early rejection of numbers that will not contribute to a better solution than what has already been found with the below check. Input, current best solution, don't proceed with a solution like 1399 or 1/400 because the optimal way to expand these solutions would be to multiply the last number by 2 repeatedly, but a larger best subset would require a final number greater than 1,000. Add to the loop large enough number to satisfy this constraint. Largest num times 2 raise the difference in solution size to the best known solution size. Yeah, which is what it did. Requires a little bit of extra time, leaving the speed the same, the space the same. And where does he put that check in? Yeah. Huh. I don't know, man. I don't know. The code that he's got going on here is a little bit kind of hard to follow, so I'm not really going too into it. But it is interesting. His is 6, but mine is only still. Respect the spacing in the if, plus right believe you're evolving. What's up, Yuki? Welcome back. Hello, hello. Welcome, welcome. How are you? How are things? Howdy. The spacing in the if, you like that? So where's my if spacing? Oh, is it this here? Did he do the same thing? He must have, right? Using a bit shift. Oh, that's my mistake. That's why. Oh yeah, no. That's no. What did he do? I think I did the right thing. He must have used a bit shift. Oh no, he multiplied. No, you don't have to do that. You can just bit shift it. You don't need. You can just bit shift this number. Because when you multiply by 2, that's what it is. A bit shift. It's kind of interesting that he. That's kind of funny. He thought to bit shift to get the power of 2 and then multiply instead of just bit shift. But anyway, that's a minor thing. How did he get 6 and I got? I'm wondering. Maybe because this requires a little extra work to do the swap and then the pop at the end. Yeah, mine's slower. It's a lot slower than his. Sad. I'm sad, you know? I'm sad. I don't know why, I don't know how I could do this more efficiently than that, though. It's kind of all I got. Yeah. It's kind of good enough for me, quite frankly. It's definitely like, I'm annoyed. Kind of annoyed. Somewhat wondering, left wondering. I don't know, man. Why is this so much faster? You know? Why is it so much faster? There's no way. No way. I don't know, man. I don't know. I'm kind of stuck trying to figure out how to make this even faster. It's basically somehow the way that he coded it, it's more efficient to do it that way rather than this way. I don't know. I don't know what it could be. I'm going to just stick with this, though. I'm going to say there's probably a way to do it that's better iteratively here, but I don't know. I don't know. It's kind of interesting. He also did it. He did it using did it recursively. Did it using a call stack. Usually the iterative version is a little bit more efficient than the recursive version because the recursive version has a lot of extra function calls, and the iterative version can be optimized by the compiler in a different way. Excuse me. Which, by the way, we can do, instead of using auto I, we can just do auto val nums. I think that works too, by the way. Excuse me. I think that's equivalent. Oh, that's a lot faster. Look at that. It's tiny optimization. Okay, yeah. So the array array accesses seem to be the issue. So in that case, we could do iterator. Yeah, actually, then let's do it that way. That might be why it's slower, faster. into ++it, and what we can do here is this possible is going to be just this iterator, access the iterator, and then we can say minus it. Let's see if that works still. Now that might not, I don't know. Oh, it does. Oh yeah, okay. Now see, that doesn't seem to be very much faster though. 28. 32. That's better. We're still kind of accessing that portion of the array though. Instead of possible to, we can use this iterator directly. Could try that. What does that do? Does that still work? That's not much faster. I'd say for legibility's sake, it's probably better to use the other one instead of using the using the iterator directly. It's kind of interesting though that sped things up. Very interesting. So now the question is, I'm still not very fast though. Still a little too slow. Right? We're expecting it to be 6 milliseconds, and it's 36 milliseconds. Still quite a bit slower than we're expecting it to be. I don't know. I couldn't say. It's definitely gotta be like, because we're swapping and popping here. That's gotta be it. That's gotta be the reason, because I think with the other solution, basically you don't need to pop and swap or swap and pop. You just break, and then the function sort of returns and doesn't continue, I guess, down that path. The pruning is a lot more efficient, I want to say. I mean, we're talking like milliseconds here, right? Like this is like super seriously tight efficiency that we're looking at. Shaving off a few milliseconds. But I don't know, man. I'm kind of like annoyed that I didn't get 6 milliseconds for writing the iterative solution. Trying to shave off as much as I can, but I think that's all I got. All right. We'll move on. Spent enough time on this. All right. Okay. Fair enough. Anyway. We did pretty good the first time around. We got 48 milliseconds, so from there we shaved off 20 milliseconds with the extra pruning. I think you have to code it a special way to get the real benefit from the pruning. I want to say something like that. Anyway, okay, all right. So yeah, let's move on to the next one. So yeah, thank you for watching this solution, this problem. Obviously we did this already yesterday, but I took a look at the discussion. I thought about the discussion and realized like, oh, there's more to it, and I felt like I wasn't really doing it justice to just move on. And I also thought like, hey, how could I program that iteratively, the pruning? If I wanted to do it recursively, it's basically the same idea, except you would do it using a like a kind of a backtracking algorithm type of thing. Instead, the backtracking would be you can make it more efficient instead of it being sort of exponential time. There's sort of ways to make it like a dynamic programming. I think the memoization is what makes it quadratic instead of exponential, and then from there you can prune off, excuse me, some of the calls using the same logic here. So, all right, let me go. I'm going to take a couple minutes and then do the next problem. So yeah, thank you all for watching, and take care. Talk to you soon, or I'll be back soon.